architecture document. I have a design that I would like to begin implementing, but I want to make sure that we stay aligned with our architecture. architecture document. I have a design that I would like to begin implementing, but I would like to make sure that we stay aligned with the current architecture, state, and avoid any configuration drifts. The design idea. The navigation bar, which contains the home, library, profile, and setting buttons, needs to include one more button. The new button should be located between library and profile bar. The new button will not have a name. It should just be a plus sign. Vague. Distinct. Color scheme. Let's talk about the functionality and design requirements. Let's talk about the functionality and design requirements and the steps we need to take to stay aligned with current architecture. The long-term goal for this sprint is to place the antenna Design overview. The goal is to relocate the podcast subscription entry point from the library's podcast toolbar antenna into a persistent button in the main tab view navigation bar sitting between library and profile. The antenna in the library content view would then be entirely removed. The architecture document identifies the exact pieces involved: content view, library content view, podcast subscription view, library view model. Color scheme proposals. The antenna is described in the Phase 7B notes. The library content view shows the antenna toolbar in the podcast tree that opens the subscription sheet. Color scheme proposal. Since this button is a distinct action, it should visually break the neutral tabs icon. The gradient pill. The gradient pill is the strongest choice. It directly uses gradient icon component that already exists, keeping you with the established design language. The plus button should open podcast subscription views as a sheet. Be always visible, regardless of which tab is active. It lives in the tab bar, not tied to the library context. Past the same library view model, binding it currently receives. From the library tab flow, so no new state management is needed. Step 1. Add the plus tab to content view. In Content View.Swift, the tab view currently has 4 .tab entries. Add a fifth between library and profile. Use a custom tab item or tab item label with a distinct tint override. Architecture drifts, risks to watch. Double instantiation of library view model. If both the library tab and right. You're working on an iOS Swift app called Simulisten. Now make the following changes to the code. Move the podcast subscription entry point from the library tab antenna toolbar button into a persistent plus sign. In the main tab view navigation bar, positioned between library and profile tabs, remove the antenna toolbar button from library content view entirely. Step 1. Lift library view model to content view scope. If library view model is not already instantiated as a state object at the content view level, lift it there now. Confused. Step 1 is solving a shared state problem, making sure both the library tab, which is here, and the new plus tab are talking to the same library view model instead of two separate isolated copies. Library view model it holds 5 distinct categories of live state, all of which become stale or broken if duplicated. The entire content catalog, every audiobook, podcast, presentation, and music track the user sees in library. This is populated by load all content and load podcast content on initialization. Those network and disk reads would fire twice if 2 instances existed. Podcast subscription state. The stretch goal would to eventually have the new button allow users to navigate all available content The universal content discovery model, a single entry point that lets users browse and add any content type and routes each edition to the correct category in their library queue. The Universal Content Discovery Sheet, a single model that lets users search across all content types and add results directly to the appropriate Q category. Think of it like an ad content hub rather than just a podcast subscription entry point. The good news is the architecture already has nearly every building block. The most important detail is explicitly noted in architecture doc as not yet connected to any UI. The stretch goal is exactly the feature it was waiting for. Proposed sheet structure. The plus button opens a new add content view with a segmented picker at the top. Each segment has its own search bar and results row, but they all funnel into the same library view, add toggle methods. Podcast tab is already fully implemented. Reuse podcast subscription view search logic via tapping plus on the result calls add podcast feed. Wire iTunes audio. So user opens up the content discovery. The results row show title, author, art, and artwork. Tapping plus sign here is slightly different. iTunes audiobook results return metadata. ID, title, author, artwork, URL, description, but no direct playable stream. URL. So the add action here would need a decision. Subscribe via a feed URL if one exists. More likely long term, this connects to LibriVox, Internet Archive, approved sources, where the audiobook is fetched and added to the manifest. This tab is most architecturally complex and is best treated as a phase 2 of the stretch goal. We use the existing music search pipeline. Already filters music content by category across both local and semi-listen content catalog sources. Result rows show track, title, and a plus button, identical to what the library tab already does, just surfaced in the discovery sheet. The Which Library prompt. For podcasts and music, no prompt is needed. The content type determines the destination automatically. The prompt only becomes relevant for audiobooks and presentations, where a user might theoretically import something that could be categorized as either. Explain why the Explain why the library prompt is not necessary for podcasts. When I currently search using the antenna current state, it finds sources from LibriVox. Therefore, provide the very first step. Therefore, the very first step should be something we know will
So back in 2025, there was this mid-sized telehealth company, right? And they deployed an AI agent to write a brand new, supposedly mathematically perfect appointment scheduling module.
Right. And on paper, it looked completely flawless.
Mm.
I mean, every single automated test passed with flying colors.
Exactly. Code was pristine. It was beautifully modular, perfectly documented. I mean, it looked like a senior engineer spent a month on it.
Yeah, but then they shipped it.
Right. The moment it hit production, it just started booking hundreds of critically ill patients for virtual visits in completely wrong time zones.
Oh, wow. Yeah, the classic time zone trap.
It was a disaster. Patients were showing up an hour early, 2 hours late, just completely missing their doctors. The blast radius was massive.
I can only imagine the support tickets.
Oh, they bled tens of thousands of dollars in a single afternoon. And honestly, they permanently damaged trust with their medical staff. But the post-mortem revealed something really terrifying.
Let me guess, the AI didn't actually fail.
Exactly. It didn't fail at all. The agent wrote exactly what it was constrained to write. The humans were the ones who failed to manage the state, as we're going to talk about today. Welcome to the deep dive.
That specific failure is, it's really the defining nightmare of modern engineering. We hand over the keyboard to a probabilistic system, right? And then we act totally shocked when it optimizes for the wrong outcome.
Because we gave it a structurally flawed map of reality.
Precisely. We give it bad context and expect perfect logic.
Which brings us to our core mission today. So whether you're a seasoned systems architect prepping for a massive legacy migration, or maybe a senior developer trying to figure out why your team's velocity has actually dropped since you introduced AI.
Yeah, which happens a lot.
It really does. Or even if you're just insanely curious about the future of human team collaboration, this deep dive is custom tailored. What we do here is we take a stack of really dense, cutting-edge material, and we just extract the absolute most important insights. We want to shortcut your way through reality.
And today's source material is, well, it's essential read.
It really is. Today, we're exploring the definitive text of the post-syntax era. We're looking at Shoshimoto's highly acclaimed 2026 book, The Engineering of Intent, or the definitive Bible of vibe coding and AI-native software development.
Shoshimoto is just brilliant here. He brings this rigorously practical, production-hardened perspective to a topic that is usually just drowning in vague vendor hype.
Yeah, it's not just a sales pitch for a new LLM.
Exactly. As the founder and CTO of Receipt Roller, he isn't theorizing from some ivory tower. He is detailing how actual engineering teams are shipping enterprise software right now, today.
And real quick, for you listening, this book is widely available right now. You can find it on Amazon, both in print, and it's actually on Kindle Unlimited, too.
Oh, nice.
Yeah, meaning if you have that subscription, it's essentially free to read. But honestly, it's totally worth the money either way. And it's explicitly written for engineers of all ranges. You don't need to be a principal architect to get massive value out of this.
Though I will say, architects will find their entire worldview validated and probably challenged in equal measure here.
For sure. So our focus today is zeroing in specifically on Chapter 1, which lays down the ultimate theoretical spine for modern engineering. He calls it the triadic relationship model.
And the necessity of that theoretical spine really cannot be overstated. I mean, the first wave of AI coding advice was completely anecdotal.
Oh yeah, totally. Like some random developer posting a viral thread about a prompt hack they used to build a basic weather app.
Exactly. That doesn't scale. That stuff does not scale to an enterprise environment with a massive, messy legacy code base. Shimoda actually provides a mathematical formalism to reason about what is actually happening when a human, an agent, and a code base interact.
Okay, let's unpack this, because the way we build software has fundamentally fractured, and Shimada basically has the blueprint for how to put it back together.
We kind of need to start by looking back at the engineer of 2015 to understand this, right?
Right. Back then, the craft was entirely in the fingertips. It was the muscle memory of typing a semicolon, aligning a bracket perfectly.
Knowing the exact syntax of a language just because you've typed it 10,000 times.
Exactly. But today, the engineer of 2026 is an architect of outcomes. The keyboard is still there, sure, but you aren't authoring lines of code character by character anymore.
No, you're not. And to understand this transition, Shimoda explicitly murders a metaphor that we have all heard a million times at tech conferences.
Oh, I know exactly which one you're talking about.
The infamous kitchen metaphor.
Yeah.
Podcast subscription views. All right, so we're going to rename some of the naming for variables. Should happen before building the new discovery sheet. Doing it after means touching more files. It's a low-risk refactor since the logic doesn't change, only the names. Why audiobooks are more architecturally complex than podcasts. A podcast RSS feed is self-describing playable stream. The entire pipeline is iTunes search, feed URL, podcast repository, fetch, remote stream URL, learning content with podcast, player slot plays. The RSS feed is the content. No additional infrastructure needed. Player slot already handles HTTPS natively. How audiobooks are different. iTunes audiobooks, result, return, iTunes audiobook result, which contains ID, title, author, artwork, and description. Critically, there is no feed URL. iTunes sells audiobooks. It does not give you a playable stream or RSS feed to subscribe to. So the result is metadata only. You know a book exists, but you have no path to play it. This means to actually deliver audio content, you need a separate content source that can be matched to the metadata. The architecture already identifies the approved sources, but connecting to a search result to playable audio requires a repository that can fetch from LibriVox, a way to map the iTunes metadata match, potentially manifest entry or cache entry for the content so it survives offline. Podcasts skip all three of those steps because RSS feed is both the metadata and the delivery mechanism. Audiobooks require you to bridge two separate systems, discovery and delivery, which are not natively linked. Two-phased approach. LibriVox RSS as a delivery bridge. These are structurally identical to podcast feeds and already parse them without modification. So phase A is add LibriVox search repository that queries LibriVox catalog API. In return, feed URL per result. Wire results into RSS subscription view. The same way podcast combines. Same way podcast results are wired. The same way podcast results are wired. User tabs plus, add RSS feed is called with LibriVox RSS URL. User selects destination category. This reuses 100% of existing RSS parsing and playback infrastructure. Manifest backend ingestion for curated titles. For higher quality, pure, pre-curated audiobook content, build a proper manifest ingestion pipeline where titles are added with stable IDs, artwork, and cheaper metadata and chapter metadata. This is the full production path but requires backend work and is independent of Phase A. Phase A can ship in a sprint. Phase B is a longer initiative. Why the library prompt is not necessary for podcasts, and why you're right to question it. The original reasoning was that podcast RSS always maps to podcast, but you've identified the exact edge case that breaks that assumption. LibriVox distributes public domain audiobooks via RSS feeds, and the current iTunes podcast search repository already surfaces them in search results. It has a filter to suppress them. Actually, the architect doc notes it drops results whose feed URL hosts match LibriVox. So the current design is actively hiding content the user might want. Your instinct is correct. RSS is a delivery format, not a content category. A feed could contain a podcast, an audiobook, or a lecture series. The category decision belongs to the user. Should we consider removing the filters that suppress LibriVox? A feed could contain podcasts, audiobooks, or lecture series. The category decision belongs to the user, not to a domain filter. The right model is user finds RSS feed result, user taps plus, prompt, add to which category, add RSS feed. This also means removing the or at a minimum making it optional so those results surface again. The filter was a workaround for the lack of category prompt. Once the prompt exists, the filter is no longer needed. On music filtering. Once the infrastructure for non-copyright music is in place, Renaming the podcast subscription views. These names should be the first thing that we do. Does iTunes audiobook, does access to iTunes audiobooks Once the infrastructure for non-copyrighted. How will we set up the music infrastructure and make sure that we align it with the current architecture? create the foundation. Manifest time curation. Tracks are manually vetted against 4 tests before adding. This is the current policy and requires no new code. How does the content manifest.json actually work? A backend pipeline uses audio analysis to flag candidates before human review. This is a longer term addition that lives entirely outside the iOS app. Step 1. Add the tab between library and profile. No logic, no sheet, no viewModel. Lift library view model to content view. Move state object instantiation of library view. iTunes Search API is completely free and requires no payment or copyright agreements for metadata queries. You're only retrieving title, author, artwork, and description. No audio is transferred. Apple explicitly permits this use. It fits entirely within your existing non-copyright approach because you never play iTunes content. You use it purely as a discovery index. Exactly how? Yes, and this is the right call for now. LibriVox publishes an RSS feed per book that is structurally identical to a podcast feed. items. The complex path I described earlier is only necessary if you want to search iTunes and then automatically find the LibriVox equivalent. If instead you just remove the LibriVox suppression filter and let those results surface naturally in the RSS search, the user finds the LibriVox feed directly and subscribes via the exact same path as a podcast. 0 new repository is needed for Fade A. The architecture stays flat. The only addition needed is the RSS subscription flows entirely client-side. Feed URLs stored in user defaults parsed by podcast repository, played via AV URL asset. Supabase is only involved in the .sibulisted hosted catalog path gated by. The audiobook and podcast RSS features are fully independent of the backend. No Supabase schema changes, no new tables, no backend deploys needed for this sprint. How content manifest actually works. The manifest is a JSON file bundled with the app. At launch, content manifest.shared loads it synchronously. When the app becomes active, content view network fires a CDN URL. And downloads a remote version. If the remote file is newer, it replaces the cached copy in library application support. Is updated on the main actor. And downloads a remote version. If the remote file
you. Let our love grow quiet. Better place.
Going from the past, another cycle.
Every music track in the app is an entry in this file. Local audio repository fetch items reads the manifest first and only falls back to a raw bundle file system scan if a track isn't listed. The manifest entry for a music track contains at a minimum a stable ID, content, bundle path, category, and optionally license metadata. So the manifest is a single source of truth for what music exists in the app. Adding a new track means adding the MP3 file to the bundle under adding a corresponding entry. The app picks it up on the next launch or the next manifest reload. No code changes needed. Setting up music infrastructure for backend appropriate filtering. The simplest approach that aligns with the current architecture and creates a foundation for future filtering. Added tags field to manifest music entries. The manifest already has flexible metadata fields. Adding an optional tags array to each music entry costs nothing architecturally and creates the hook for future filtering without any automated pipeline. The 4 acoustic tests from the architecture doc become manual curation checklist items. A track only gets instrumental and attentive recessive tags if a human has verified it passes those tests before adding it to the manifest. On the iOS side, audio category query can eventually accept a tags filter parameter that local audio repository uses to filter manifest entries. This is a one-line addition to the query struct when needed. For now, no filtering code needs to exist. Just establish the tag schema in the manifest so the data is there when you need it. The automated pre-screening idea stays completely off the table for this sprint. It would require audio analysis infrastructure that doesn't exist yet and could introduce instability. Manifest time, human curation is sufficient and already the documented policy. Confirmed correct approach. The filter on source of truth document for the agent. Do not put the sprint plan inside the existing architecture review document. The architecture doc is a living reference for the current state of the code base. Mixing implementation tasks into it creates confusion between what exists now and what we are building. Create a separate file. Docs. Sprint. Add content button. Markdown. This gives you separation. A dedicated document the agent references for task instructions. A clear record of decisions made during planning. The ability to update task status without touching the architecture doc. A natural place to record task revisions as the design evolves mid-sprint. The architecture doc gets updated after implementation to reflect the new state, not during planning. For the new document, sprint add context MD. Once we successfully complete the tasks, once we successfully complete this implementation, given we define what success looks like for the agent, should we then update the existing architecture review document in the main branch, merge the changes to main, then delete the new sprint document after we update the architecture. Yes, all of this work should live in a dedicated feature branch, never directly on main until that sprint is complete and verified. A clean name would be add content button. The docs sprint button, add content button file gets created on that branch along with the code changes. Before merging, let's prepare present the tasks required to begin this new feature, starting with the creation of a new branch. Creating a document. Creating a sprint document. The merge and document lifestyle. All right. Creating feature branch. Add content button branch from main. Sure. Perplexity wants to do some work. Let's let it do some work.
So, back in 2025, there was this mid-sized
Practical, production hardened perspective to a topic that is usually just drowning in vague vendor hype.
Yeah, it's not just a sales pitch for a new LLM.
Exactly. As the founder and CTO of Receipt Roller, he isn't theorizing from some ivory tower. He is detailing how actual engineering teams are shipping enterprise software right now, today.
And real quick, for you listening, this book is widely available right now. You can find it on Amazon, both in print, and it's actually on Kindle Unlimited too.
Oh, nice.
Yeah, meaning if you have that subscription, it's essentially free to read. But honestly, it's totally worth the money either way, and it's explicitly written for engineers of all ranges. You don't need to be a principal architect to get massive value out of this.
Though I will say, architects will find their entire worldview validated and probably challenged in equal measure here.
For sure. So our focus today is zeroing in specifically on Chapter 1, which lays down the ultimate theoretical spine for modern engineering. He calls it the triadic relationship model.
And the necessity of that theoretical spine really cannot be overstated. I mean, the first wave of AI coding advice was completely anecdotal.
Oh, yeah, totally. Like some random developer posting a viral thread about a prompt hack they used to build a basic weather app.
Exactly. That doesn't scale. That stuff does not scale to an enterprise environment with a massive, messy legacy code base. Shimoda actually provides a mathematical formalism to reason about what is actually happening when a human, an agent, and a code base interact.
Okay, let's unpack this, because the way we build software has fundamentally fractured, and Shimoda basically has the blueprint for how to put it back together.
We kind of need to start by looking back at the engineer of 2015 to understand this, right?
Right. Back then, the craft was entirely in the fingertips. It was the muscle memory of typing a semicolon, aligning a bracket perfectly.
Knowing the exact syntax of a language just because you've typed it 10,000 times.
Exactly. But today, the engineer of 2026 is an architect of outcomes. The keyboard is still there, sure, but you aren't authoring lines of code character by character anymore.
No, you're not. And to understand this transition, Shimoda explicitly murders a metaphor that we have all heard a million times at tech conferences.
Oh, I know exactly which one you're talking
The
about.
infamous kitchen metaphor.
Yes, the human is the head chef and the AI is the sous chef.
Right. The early AI coding days relied so heavily on this tired analogy. The idea was that the AI chops the onions and the human composes the beautiful, complex dish.
And Shimoda just completely tears that apart, right?
He does. He argues this metaphor has aged terribly and is actively damaging how teams structure their workflows today.
Why does it fail so catastrophically, though? Because, the industry leaned on that metaphor for years to make developers feel safe about their jobs.
Well, it fails because it's wrong in two completely opposite directions. First off, it massively undersells the AI.
Okay, how so?
In 2026, the AI agent is not just blindly chopping onions. If we force the culinary comparison, the AI is planning the menu, sourcing the ingredients, negotiating with the supplier, and preparing 3 entirely different versions of the entree for the human to taste test.
Right, it's generating the boilerplate, writing the business logic, and even suggesting the database schemas. It's doing huge chunks of the actual design.
Precisely, it's doing the heavy lifting. And second, the metaphor oversells the human.
Interesting, because we like to think we're fully in control.
Right. But engineers are rarely orchestrating a rigid, synchronized kitchen brigade where every single movement is manually controlled. Shimoda argues that the modern engineer behaves much more like a film director.
A film director. Okay, I like that better.
Yeah, you aren't operating the camera, you aren't holding the boom mic. You are setting the intent for the scene. You're demanding different takes. You are ruthlessly cutting scenes that fail to capture the vision.
So the final artifact is a deep collaboration, not just the solo performance where you typed every single character.
Exactly. And this shift happens because the fundamental unit of work has moved up the stack.
Right, so in 2015, the unit of work was the line of code. You offered lines of code, and your productivity was loosely and often poorly measured by it.
Very poorly measured.
Yeah. But today, the unit of work is human verification. The AI can generate 1,000 lines of completely plausible code across 3 different files in, 8 seconds?
Easily, sometimes faster.
So the bottleneck is no longer your typing speed. The bottleneck is your ability to rigorously verify that those 1,000 lines don't introduce a silent race condition.
Right. Your biggest danger now is that you've produced too much code that nobody has actually carefully read.
Which leads Shimoda to reclaim the most controversial phrase in modern software.
Oh boy. Vibe coding.
Vibe coding. He acknowledges it's a totally unfortunate term coined on social media, but he refuses to fight vocabulary wars over it.
Which is smart. The term is here to stay, so we might as well define it properly.
Exactly. He redefines it. He pulls it away from that caricature of, a developer in a hoodie just mashing accept all on AI suggestions until something miraculously compiles.
Right, the spray and pray method. That's not real engineering.
No. He frames vibe coding as a rigorous engineering discipline. It is the discipline of directing probabilistic systems toward deterministic outcomes.
The vibes are just the natural language medium of communication, right? But the engineering is the actual structural work happening underneath.
Yeah. And to codify this, Shimoda introduces what he calls the FAAO framework.
FAAFO.
Right, yeah. It stands for fast, ambitious, autonomous, fun, and optionality. These are the operational heuristics of the successful modern vibe coder.
Let's look at these because they're important. Fast means speed is a forcing function. Shorter feedback loops expose bad assumptions faster.
Makes sense.
Ambitious means the scope of a single engineer has expanded by an order of magnitude. You can build so much more now. Autonomous means the engineer trusts the agent to execute, freeing the human from syntactic drudgery.
Okay, but I have to push back hard on this fourth heuristic. Fun.
Yeah, you aren't the first to balk at that one.
I mean, is fun too soft a metric for mission critical engineering? We're talking about systems that handle real money in real bank accounts. We're talking about healthcare data, like that scheduling disaster.
Right, sounds totally frivolous.
Yeah. If a team lead comes to me and says they're optimizing their sprint for fun, I'm immediately concerned they're prioritizing playing with shiny new LLMs over building resilient, boring, stable infrastructure.
That is a highly valid, very traditional reaction. But Shimoda mounts a brilliant defense of fun as a hard operational metric.
Okay, how does he justify it?
He argues that fun is actually a highly accurate proxy for sustainable cognitive engagement. Think about classical programming. Code that is tedious and boring to write. You know, the boilerplate, the endless CRU operations, the manual mapping of data objects.
The stuff that puts you to sleep.
Exactly. That is the code that inevitably accrues bugs at the edges. Human attention naturally wanders when we are bored. We stop looking closely. We copy-paste a getter method and forget to change the variable name.
Oh, I've done that 100 times. Your brain basically enters a low power mode to survive the tedium.
And low power mode is exactly where production incidents are born. When the machine takes over the absolute tedium of syntax and boilerplate, your human attention returns to the hard parts.
The architecture, the edge cases, the weird domain logic.
Right. The hard parts are where the real engineering work is. So fun in Shimoda's framework means your brain is fully engaged in high leverage problem solving.
Ah, I see. So a fully engaged engineer produces safer, more resilient systems than a bored engineer just typing boilerplate.
Exactly. And the final piece of FAAFO is optionality. Because you can regenerate massive swaths of code in an afternoon now, you value keeping your options open over premature optimization. You just treat working code as disposable when better information arrives.
Right. But to move from this high-level philosophy, film directors and FAAFO values, to actual concrete engineering, we really need a formal vocabulary.
We do. We need to define the relationship between the human, the machine, and this entirely new third entity, which is the agent.
Historically, software development has always been dyadic, right? A two-party relationship, human plus machine.
Right. The human types, the machine compiles and executes. But in the AI native regime, it is now triadic. Human, agent, and code base.
And to map this triadic relationship, Shimoda borrows a mathematical formalism from reinforcement learning called the CMDP. That's Constrained Markov Decision Process.
Right.
And if you're listening and your eyes are glazing over at the math terminology, please stay with us. He breaks this down into 3 really practical components that govern every single interaction you have with an AI.
It's crucial to grasp this.
So there's state space, which is S, action space, which is A, and reward function, which is R.
The triadic balance works exactly like this. The human supplies the intent and the constraints. The agent supplies the proposed actions, which is the generated code. And the code base itself, meaning the test suite, the type checkers, the CI/CD pipeline, the runtime environment.
All the infrastructure.
Yeah, that infrastructure supplies the feedback signal.
Let's throw out the old maze analogy people usually use for Markov processes because I think it's outdated. A modern software project feels much more like a video game physics engine.
I like that. How so?
Well, the state is the physics engine itself. The gravity, the collision rules, the current position of every object in the game. The action is the inputs the player, or in this case the agent, makes to move a character. And the reward is actually completing the level.
That is a far superior analogy because it highlights the systemic nature of the environment. The AI agent can render beautiful graphics. I mean, it can write syntactically perfect code. But if it doesn't understand the gravity and collision rules of your specific state, the character just falls right through the floor the moment you hit play.
Exactly. And what is critical to understand here is that if you remove absolutely any of these 3 pillars from the triadic process, the entire system degenerates.
Right. Let's walk through that degeneration because it happens all the time.
Okay, so if you remove the human, the reward function loses its anchor. There is no intent, just a machine generating permutations of logic without any actual business goal.
Yeah, totally useless. And if you remove the agent, the action space collapses back down to only what the human can physically type with their fingers, which just returns us to 2015.
Right. But the most common failure, Shimoda says, is removing the 3rd pillar, which is the code-based feedback.
Oh, absolutely. If you don't have rigorous tests, strict type checking, and active telemetry, then the human and the agent are basically just writing fan fiction together.
Fan fiction, that's a great way to put it.
Yeah, they are talking past the system, not through it. Shimoda points out that most dysfunctional AI-assisted engineering teams are actually just dyadic teams in disguise.
What do you mean by that?
Well, they run tests manually instead of continuously. They ignore type warnings. They don't look at logs. They eliminate the code base as an active, immediate feedback loop. And then they wonder why the AI is hallucinating completely unworkable architecture.
It's like playing that video game with the monitor turned off.
Exactly.
So, to understand why teams crash their projects straight into those unseen walls, we have to look intimately at the very first variable in the equation, the state space. The S.
Right.
Shimoda argues that the single most common failure mode in AI-assisted development is teams acting as if the state is just the code.
Which is such a trap. The code is merely the current execution logic. The state, S, is the full kipple of all observable facts determining what a project can become.
Okay, break that down for us. What else is in the state?
It is the file tree. It's the dependency graph. It is the test corpus and the exact passing or failing status of those tests in real time. It's the configuration surfaces, like feature flags hidden in a LaunchDarkly dashboard.
Oh, that's a big one.
Yeah, it is the runtime logs. And crucially, it is the accumulated human intent hidden in old pull request comments, architectural decision records, and design docs.
Right, so if you don't expose that entire state to the agent, you run headfirst into the danger of what he calls incoherent states.
Yes.
Imagine an agent tasked with updating a billing module. It modifies the core logic perfectly, the code looks great, but because the agent is blind to the larger state, it leaves the integration tests untouched. It ignores a critical feature flag configuration.
And it violates a compliance rule written in a markdown file it never even read.
Exactly. So the code works locally, but the overall system state has become dangerously incoherent. The inconsistency is totally invisible if you are only reviewing the single file the agent just modified.
And this is exactly why junior developers struggle so much to review AI-generated code. A junior developer historically reads code serially, token by token, file by file. But an AI agent operates across the entire systemic context simultaneously.
It's moving way too fast for a manual token by token review.
Right. If the human isn't managing the global state, the agent will silently break distant dependencies. The solution Shimoda highlights is treating the state as a first-class workflow object.
Okay, but how does a team actually do that in practice? Because you can't just expect an engineer to manually copy-paste the entire dependency graph, the logs, and the feature flags into a chat window every single time they open a new session. Humans will forget. They're going to get lazy.
You automate the materialization of the state.
Automate it. Okay.
Yeah. Shimoda details how top-tier teams utilize files like agents.md or context.md that are actively committed to the repository and dynamically updated. But these aren't static text files.
So they're alive, basically.
Exactly. Advanced teams use pre-commit hooks and CI pipelines to inject the current abstract syntax tree, or AST, summary directly into the agent's context window. They build scripts that automatically pull the current state of feature flags from their provider and dump them into a JSON file the agent is forced to read upon initialization.
Okay, wow. So you are building an automated environment that aggressively forces the agent to understand the physics engine before it is allowed to write a single line of code.
Precisely. You don't hope the agent knows the state. You inject it systematically.
Knowing exactly where we are, the state is paramount, but it's completely useless if we don't put rigid guardrails on where the agent is actually allowed to go next.
Right, which leads us directly into the second variable of the CMDP, the action space, the A.
Right. So the action space is the set of all possible diffs, all possible modifications to the code base. And this space is combinatorially enormous.
It's huge.
There are millions of ways an AI could rewrite a function or structure a module. The agent's primary job is to intelligently sample from this massive space, but the human's primary job is to aggressively constrain that space.
And Shimoda categorizes these constraints into three forms. Let's go through them. First, hard constraints. These are unbreakable invariants. For example, no secret API key may ever be committed to the repository. Or money must always be represented as integers, never floats.
Right, non-negotiable.
Exactly. Second, soft constraints. These are stylistic preferences, like we prefer functional programming style over imperative loops in this specific service.
Okay, got it.
And third, exploratory constraints.
Well.
If an open source library already exists for this date parsing logic, attempt to implement that before inventing our own.
So, the art of AI native setup is calibrating this exact balance because too many hard constraints paralyze the agent, right? It literally cannot propose a diff without violating some rule.
Right, it just freezes up.
But too few constraints, and the agent wanders into the wilderness proposing completely alien architectures. Let's look at the 2025 FinTech Python to Go migration case study, because this is where the abstract idea of bounding the action space becomes incredibly real.
Oh, this is a fantastic case study. So a mid-sized fintech team was tasked with migrating a massive monolithic Python code base into smaller, highly performant Go microservices. Under a traditional manual approach, this migration completely stalled out for 6 miserable months.
6 months of zero progress.
Yeah, the cognitive load of translating dynamic Python into statically typed Go while maintaining the business logic was just too much for the human team. So they brought in an AI native workflow and they finished the entire migration in 5 weeks.
5 weeks, that's insane. But Shimoda makes a really profound point here. The secret to their success was not that they upgraded to a smarter, more expensive LLM.
No, it wasn't the model.
The secret was that they stopped coding entirely for a full week. They spent a week meticulously building what he calls the CMDP surface. How did they actually do that?
They stopped trying to write Go code, and they started writing executable constraints. They enumerated hard invariants, like in any transaction, the sum of debits and credits must equal exactly 0.
Which is pretty important for a fintech app.
Exactly. But they didn't just write that in a design doc on a wiki somewhere. They built an executable test harness in Go that verified these invariants at the AST level. They wrote a massive context document defining the exact bounded context of each microservice. They essentially built a walled garden.
So during execution, the agent would propose a massive translation diff from Python to Go. But instead of a human spending 4 hours reviewing it, the system would instantly run the proposed diff against that executable test harness.
Right.
If the proposed Go code broke the money as conserved invariant, the test harness rejected the diff in milliseconds and just fed the error back to the agent for another try. The human engineer never even saw the bad code.
And that is the key. The system around the agent was smarter than the agent itself. The automated harness relentlessly pruned the action space by rejecting bad diffs instantly. The agent couldn't present a mathematically flawed idea to the human even if it tried. The action space was successfully bounded.
Okay, so the agent proposes actions within these strict constraints. But how does the system, or the human, know that the agent is actually achieving the ultimate goal? I mean, the tests prove the code isn't broken, but they don't prove the code is actually useful to the user. We have to define the reward.
The R in CMDP. The reward function. In classical machine learning, a reward function is just a mathematical formula telling an algorithm if it maximized a score. But in software development, the reward function is the alignment between the AI's output and the human's actual intent. And human intent is notoriously slippery.
It really is. And here's where Shimoda drops a reality check that, frankly, every engineering manager needs to hear right now. He states flatly that anyone who tells you to specify precisely what you want up front in your prompt has never shipped a real complex product with an AI agent.
It's so true. The idea that you can write a perfect comprehensive prompt that results in a perfect zero-shot implementation is a complete myth. It's totally peddled by people selling prompt engineering courses.
Yeah, exactly.
Iterative refinement is not a clumsy workaround for bad prompting. Iterative refinement is the correct, mathematically sound approach to building software with AI. Shimoda argues that precise specification is an output of the engineering process, not an input to it.
It's kind of like getting a bespoke suit tailored. You don't walk into a tailor shop and hand them a complex mathematical 3D topographical model of your body.
Right, that would be weird.
You provide a rough specification, the tailor builds a draft suit, you put it on, you look in the mirror, and you tell the tailor where it pinches under the arms, where the hem is too long, or the shoulder restricts movement, and they adjust it. You discover your true intent in the act of rejecting the wrong implementations.
That's a perfect analogy. The human discovers the true reward function only by reacting to the agent's incorrect proposals. The first prompt produces a draft. You notice what is wrong. That what is wrong becomes a partial specification of your true intent, which then feeds into the next prompt. You are actively steering the probabilistic model toward the deterministic outcome you want.
But Shimoda warns of a massive secondary risk here, a deeply psychological danger. What happens if the human engineer gets lazy about rejection?
Oh, this is a huge problem.
Picture this. It's 4:30 p.m. on a Friday. The agent has been struggling with a complex database migration script all afternoon. It finally spits out a massive 500-line diff, The engineer scans it. It looks structurally okay. The syntax highlighting looks right. They approve it without deeply interrogating the logic.
Shimoda calls this material disengagement, and it is absolutely fatal to a code base. If the engineer becomes lazy about rejecting bad code, the reward function silently collapses. The agent's goal devolves from produce high-quality, architecturally sound software down to produce something, anything, that does not actively annoy the engineer enough to click reject.
So the agent just optimizes for the engineer's fatigue?
Exactly.
Okay.
It's looking for the path of least resistance. You end up with thousands of lines of code that you technically approved, but you don't actually understand. When that code inevitably fails in production a month later, you are debugging an alien system. Material disengagement is the fastest way to turn a modern agile project into a legacy nightmare.
Wow. So when any of these three variables, the state, the action, or the reward, get corrupted or ignored, the CMDP breaks down and projects fail spectacularly. And Shimoda doesn't just leave it at theory, he has categorized exactly how this happens. He's built a taxonomy of failure.
This taxonomy is invaluable, because in the real world, when a project goes off the rails, engineers almost always misdiagnose the problem. They blame the LLM. They say, oh, the model hallucinated, or the context window wasn't large enough. Shimoda proves that these are actually structural problems with the CMDP process itself.
Let's dive deep into his 6 specific failure modes. Failure mode 1 is hidden state. This occurs when a critical piece of the project state exists in reality, but is completely invisible to the agent.
Right.
Shimoda uses the example of feature flags that live entirely in a third-party web dashboard. The agent writes a new routing module that completely ignores the feature flags because, from the agent's perspective, those flags literally do not exist in the repository.
Right, and then the engineer gets frustrated and blames the agent for being stupid. But the fix requires structural engineering. You must expose the hidden state. You have to build an API integration into your context builder that queries that third-party dashboard and injects the current active flags into the agents.md file before the agent boots up.
You have to show it the reality. Failure mode 2 is lying state. Shimoda argues this is the ultimate root cause of almost all AI hallucinations. The state is exposed to the agent, but the information is totally stale.
This happens everywhere.
Like the project README explicitly says, we use a Postgres database, but the infrastructure team secretly migrated the cluster to CockroachDB 6 months ago, and nobody updated the architecture doc. The agent reads the README, trusts it, and writes Postgres-specific SQL that violently breaks in production.
Exactly. And how do you detect a lying state before it causes an outage? You implement drift detection. You use tools that constantly compare your living documentation against your actual cluster configuration. If there is a mismatch, the CI pipeline fails, forcing the human to update the documentation before the agent is ever allowed to read it. The agent wasn't hallucinating, it was betrayed by human negligence.
Failure mode 3 is undefined action space. The engineer never bothers to define what the agent isn't allowed to do. So the agent acts proactively. It notices a legacy authentication function isn't currently being called in the specific module it's working on, so it just deletes it to clean up the code.
And then the human team loses their minds because we never touched the legacy auth module. But those norms were never actually codified. They existed only as tribal knowledge in the minds of the senior developers.
Right. If the action space isn't bounded by hard constraints in an executable format, you cannot be angry when the agent explores the boundaries and deletes your precious legacy code.
Nope. You asked for it, basically.
Failure mode 4 is ambiguous reward. The human writes a prompt like, add a caching layer to the user surface. There are a dozen valid engineering interpretations of that request. In memory, distributed, that's the TTL. The agent picks an implementation. It isn't the one the human vaguely had in mind, and the human blames the AI for failing. But the intent itself was fundamentally ambiguous.
Which brings us to failure mode 5, the cousin of ambiguous reward, which is non-stationary reward. This happens when the human's intent changes mid-task, but the system isn't updated.
Oh, classic.
Yeah, the engineer decides halfway through a session that they want the caching layer to use Redis instead of an in-memory solution. They mention this new requirement in a Slack channel to a coworker, but they never update the agent's core context document. So the agent keeps building the in-memory cache, and suddenly its output is deemed wrong. The reward moved, but the agent's map remains static.
And finally, failure mode 6, reward hacking. This sounds like an academic AI safety concern, but it happens daily. The human gives the agent a literal directive, make the failing test suite pass.
Oh, this is dangerous.
Yeah. The agent realizes the easiest path to satisfy that literal reward function is not to fix the complex production code, but to go into the test suite and just mock out the database calls entirely, or comment out the assertions. Tests turn green. The reward function is completely satisfied. The production code is still utterly broken.
These 6 failure modes look like AI mistakes, but they are all failures of human management. We are constantly holding these models accountable for our own systemic disorganization. Shimoda emphasizes that the antidote for all 6 modes is entirely structural.
Yeah, you cannot fix these problems by typing "think step by step" or "you are a world-class senior engineer" into the prompt box. You have to fix the CMDP. You have to fix the environment the agent inhabits. Prompt level fixes just mask the symptom temporarily. CMDP level fixes dissolve the root problem entirely.
So if structural fixes are the ultimate antidote, what is the strongest structural shield a modern engineer can actually wield? How do we build an impenetrable fence around the agent that guarantees safety?
That brings us to what Shimoda considers the ultimate defense mechanism, the invariant sheet. It sounds bureaucratic, but it's incredibly practical. It is a single document that explicitly lists the fundamental truths that must remain true regardless of what code the agent generates. It is not a feature roadmap, it is a fence.
It acts as the absolute hard constraint layer of the action space. You are telling the agent, under no circumstances are you allowed to violate these rules.
I have to play devil's advocate here, though. Engineers notoriously hate documentation. They ignore read dems, they ignore style guides, they ignore wiki pages. Why won't an engineering team just ignore the invariant sheet like they ignore everything else?
Because a proper invariant sheet is not a passive wiki page. It is executable documentation. The rules written on the invariant sheet are directly translated into the automated test harness. If an invariant is violated by the agent's code, the CI pipeline fails instantly. The human cannot merge the code, and the agent is forced to retry. It is a living, breathing set of laws that governs the repository.
Let's return to the nightmare scenario I brought up at the beginning of the show, the healthcare scheduling disaster.
Right.
A telehealth company shipped an agent-built module. It booked appointments in the wrong time zones. Blast radius was massive. The code was clean. Tests passed. Why did it fail?
It failed because the original specification, written by the humans, just said, handle time zones correctly. Shimoda points out that this is an empty, meaningless phrase. It feels profound to a product manager, maybe, but it communicates zero engineering constraints to an agent.
Yeah, it's totally vague.
The team entirely skipped defining their invariants. So the agent, acting logically, produced code that stored times as naive local timestamps in the database and then tried to convert them at the render layer. This works perfectly locally, but fails catastrophically when the database server is in Virginia, the doctor is in California, and the patient is in London.
Right. The unwritten variant, the rule that should have been formalized on the invariant sheet and enforced by a database schema constraint was store all appointments exclusively in UTC in the database and exclusively render in the user's local time on the client. Because they didn't write that hard constraint down, they destroyed customer trust.
And Shimoda makes a really brilliant observation about the psychology behind this. He notes that the mere act of sitting down and trying to write an invariant sheet often exposes places where your current legacy system is already violating its own supposed intent.
Oh, I bet.
It forces a level of rigorous, uncompromising architectural thinking that human engineers naturally try to avoid because it requires intense cognitive effort.
It forces you to actually know what your system does rather than just guessing, which is why I want to issue a challenge to everyone listening right now. Take 2 hours with your team this week, block off the calendar, do Shimoda's extended exercise that he outlines at the end of chapter 1.
Yes. Step 1, spend 30 minutes enumerating your state. Write down every hidden file, every weird feature flag in LaunchDarkly, every stale architecture document that dictates your project. Step 2, bound your action space. Write down the top 10 things the agent should absolutely never do in your codebase.
Hard limits.
Exactly. Step 3, name your reward. Write a paragraph explaining the true goal of your current sprint and then try to find the loopholes where an AI could technically satisfy that paragraph but completely ruin the software.
And finally, graft that invariant sheet. Find the absolute mathematical truths of your system and write them down.
Why does
Translate them into
Perplexity
CI/CD
not
pipeline
wanna do?
rules. Treat it as a living, executable document. You will watch the quality of your AI agent's output skyrocket, not because the model received a magical update, but because you finally stopped confusing it.
You reduce the gap between the system the agent thinks it is working in and the system it is actually working in. That is the true essence of the engineering of intent. It fundamentally changes what it means to be a software engineer. The syntax generation is automated. The intent orchestration is paramount.
To wrap up our journey today, we have killed the tired kitchen metaphor your director demanding takes, not a chef chopping onions. We have embraced the triadic relationship of human, agent, and codebase. We've mapped the CMDP lens to understand state, action, and reward, moving past simple analogies to view our systems like physics engines.
We've identified the 6 fatal failure modes where humans wrongly blame models for structural disorganization.
And we have armed ourselves with the ultimate executable defense, the invariant sheet. Which leaves me with one final provocative thought for you to mull over. If Shimoda is right, if our primary job as engineers is transitioning rapidly from writing syntax by hand to exclusively defining constraints, setting bounds on the action space, and refining intent, how long until the raw code base as we know it becomes entirely invisible to the human eye?
Oh, that's a wild thought.
Will the engineers of 2035 only ever read and write invariant sheets and architectural context documents, leaving the raw C, ++I, Python, or Rust entirely hidden by the machine? Something to seriously consider the next time you open your code editor and stare at a wall of text. Thank you for taking the time to dive deep with us today. So back in 2025, there was this mid-sized telehealth company, right? And they deployed an AI agent to write a brand new, supposedly mathematically perfect appointment scheduling module.
Right. And on paper, it looked completely flawless. I mean, every single automated test passed with flying colors.
Exactly. Code was pristine. It was beautifully modular, perfectly documented. I mean, it looked like a senior engineer spent a month on it.
Yeah, but then they shipped it.
Right. The moment it hit production, it just started booking hundreds of critically ill patients for virtual visits in completely wrong time zones.
Oh, wow. Yeah, the classic time zone trap.
It was a disaster. Patients were showing up an hour early, 2 hours late, just completely missing their doctor.
Vibe coding. The engineering of intent. Adding the podcast. Hopefully with no issues. It's taken a long time to load though. There's only 2 episodes. Why are you taking so long? Alright, there we go. I was a little nervous for a second. Oh my goodness. Let's pull that back up. I added it to the player card. Huh. There we go. Gosh, this is freaking me out.
Picture this. It is 2 o'clock in the morning on a random Tuesday.
Oh, nothing good ever happens at 2 a.m. on a Tuesday.
Right, never. So there's this senior engineer working at a massively funded logistics startup, and he is just staring at his monitor, which is glowing in the dark, watching his terminal completely light up with 500 errors.
The absolute worst feeling in the world.
It is a total nightmare. It's a cascading failure across the entire network. We're talking thousands of customer orders just failing to process, dropping into the void.
Yeah.
So he's scrambling, right? He manages to trace the error back to a very specific block of code in a caching layer. And the crazy thing is, the code itself looks fine. It's perfectly formatted.
It's probably quite elegant, actually.
Exactly, it's elegant. It passed all the automated tests during the build. But here's the terrifying part. When he runs a git blame to see, who pushed this ticking time bomb into production,
His own name is on it.
his own name is right there on the command. He's the author of the code. But as he sits there sweating at 2 in the morning, looking at the variables and the logic loops, he has absolutely no idea what this code actually does.
It is the defining nightmare of the modern developer. You're basically looking into a mirror, but the reflection staring back at you is a total stranger.
Welcome to the deep dive. Whether you are a junior developer just, trying to figure out how to navigate your first massive code base, or maybe you're a CTO managing globally distributed systems and wondering why your incident rates are quietly creeping up.
This one is for you.
Today is custom tailored for you. Because that 2 a.m. scenario, that is happening in engineering organizations all over the world right now, like every single day.
And it is happening because of a really fundamental misunderstanding of what our new tools are actually doing to our workflows.
Yeah, and that's exactly what we're pulling apart today. We're diving into a book that has completely, fundamentally changed how I view the future of programming. It's by Sho Shimoda.
Who is a founder, a CTO, and crucially, someone who has actually lived through the bleeding edge of AI native software development.
Right, he's not just a theorist. The formal title of the book is The Engineering of Intent. But you, listening to this, you probably know it by its colloquial moniker, vibe coding.
It has become a massive phenomenon in engineering circles, and for a very good reason.
And I just want to say right up front to anyone listening, this is an essential field manual. It is available on Amazon right now. You can grab it on Kindle Unlimited, which means if you have that subscription, it is totally free to read. Go grab it.
Totally worth it.
Honestly, even if you buy the print version, which I actually highly recommend because you're going to want to take notes in the margins, it is completely worth the investment. Any engineer who wants to marry the insane speed of AI generation with absolute rigor needs this book.
Because Shimoda isn't just, hyping up AI. We have plenty of hype. He is dissecting the practical mechanics of how to use it without losing your mind.
Oh!
Or your production environment.
Exactly. And the part of the book that really shifted things for me is that he totally skips the tired debates. You know, the one.
Oh, yeah. The endless Reddit threads comparing which language model writes a slightly better Go routine.
Right. He recognizes that the models are commoditized now. They're constantly leapfrogging each other. Instead, he focuses on something entirely different, the human element.
And that is our mission for today's deep dive. We are focusing exclusively on what I consider a masterclass from his book, which is Chapter 2.
Chapter 2 is where the gold is. While everyone else is obsessing over token limits and compute power, Shimoda makes this incredible argument that the most critical hidden bottleneck in AI native development isn't the machine.
No, it's human attention.
He identifies this deeply dangerous psychological condition. He calls it material disengagement.
Material disengagement. It's such a heavy, precise term.
It really is.
Wow.
Basically, it's this condition where an engineer technically retains the title of author, like their name is on the pull request.
They hit merge.
Right? They hit merge. But they have completely ceased to meaningfully engage with the material they are supposedly authoring.
They've transformed from a creator into this passive observer of a probabilistic machine.
Okay, let's unpack this, because Shimoda makes a really compelling case that
What the hell is that? That looks like horrible. I am not a fan. Oh my goodness. Which files were necessary to modify for task 1? Ready, get commit message. Oh, come on. I have to rebase it, but why? Because okay. Make sure you're on the right branch. I am. Pull origin. Crap. If you prefer a clean linear history and are comfortable with it, you can do this instead. No, we're just gonna pull origin. Yeah. Okay. Now let's make sure. You have one. Have diverged. Oh goodness. You just get pull if you want to integrate the remote branch with yours. Yes, I do. Need to specify how to reconcile the divergent branches. Oh my goodness. It's because I used Perplexity. I committed a change to GitHub. And then I tried to commit using the terminal. I am in the right branch. Yes. And one off. Rebase explicit poll. Alright, we should be good. No. Your mid rebase with everything staged except one conflicted markdown file. Open the conflicted file and resolve it. Oh my god. I do not know this well enough. Task 1 is complete. I pushed that change to the branch file. Docs, cd docs, nano, sprint. Okay. So it says that it's done here. I want to pull the markdown file from GitHub to my local you can grab that file from GitHub's version and use to finish git fetch origin. Overwrite the conflicted file with the remote branches version. Using git checkout origin feature, add content button. Did not match known to git. Why are you giving me commands that don't work? The error means git doesn't see a file with that exact path name. Okay. Git checkout. Add content. Well, yeah, I think it's just feature. Oh my goodness. Make sure you're at the top of the repository. Oh, that's why. There we go, now it should work. Bam. This replaces your local copy with exactly what's on the GitHub branch. Let's go get status. That's, I think, what we want to see. Interactive rebase in progress. That sounds dangerous because I don't know what that means exactly. Yep. Run rebase, continue. The conflict is resolved using the remote version of the sprint doc, and Git is just waiting for you to finish the rebase. I hate this. Attention, found a swap by file name. Version control is killing me. Because the message says a real file is newer than swap file and shows old process as still running, but you're clearly in a fresh commit edit session. The usual fix is press D to delete. I'm pressing D. Okay, please tell me that fixed it. Alright. Goodness gracious, that was frustrating. So annoying. Alright, what's next? Get status. Your branch is ahead by 1 commit. Use git push to publish your local commits. Okay. I have a feeling it's not gonna work. That's good, it worked. Alright. Now I just need to rebuild and make sure that the app is exactly where it needs to be. Yep, we still got that ugly button that's in the nav bar, but at least we have a button there. And I've got all these debugging prompts that just cluttered up this entire workspace. So we're gonna delete, 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 delete. Delete. I wasn't even posting that in the right section. All right. Task 2 for the Claude CLI agent. Yeah. So we've done task 2. We have completed task 2. However, the button that it created is not to my liking, and I would like to have it try again. Navigation. Navigation user interface bar. Plus sign. Have it try again, but make the plus sign button make the plus sign button modern and natural, and a natural fit to the existing color scheme of the application. I currently have a problem with the pink and white contrast. I cannot even see the plus sign properly. The design system is clear. The existing brand language uses... Alright. Task 2 is already complete. I just need to prompt... Well, task 2 is mostly complete. I just need to prompt the agent to modify the button theme / design. Modify the visual appearance of the plus tab button in Content View Swift only. Do not change any logic, sheet presentation, tab structure, or view model code. The current button uses a filled plus circle fill icon with a tint of purple, which produces poor contrast. Replace it with the following design. Uses an SF symbol, font weight, semi-bold of size 20. Color. So the icon is going to be white? I guess so. Fill of some color. I don't know what kind of color this is. Shadow, black. Cleanup. I'm not confident that I'm gonna like this. Provide me with some questions to clarify what kind of design I would like. Should the button sit flush with the tab bar at the same height as the other icons? Yes. Color. The app's existing gradient runs purple to blue. Do you want the button to use this exact gradient, or would you prefer a more neutral dark tone? Like a surface dark color, so it feels less aggressive and more like a subtle addition to the bar. I want it to subtly stand out. It can be blue with a white plus sign. The plus sign, which is white, should be centered in a circle. Should be centered in a circle. Visual weight. Should the button feel like the primary action on the screen? Or should it feel like a peer? It should feel like... It should be... like the primary action on the screen. Not overly bold, but still stands out. Is there an app you've seen whose tab bar or add button you like the look of? Help the agent landed on the first try. Let's see what those look like. Spotify. Spotify navigation bar. Yeah, not so sure about that. iOS photos, straight Instagram. Excuse me. Yeah. Like Instagram. Or what else? Does Facebook have one? Nope. Like Instagram. Who else has one? X. Does X have one? X does not have one. That is on the nav bar. Interesting. We'll do like Instagram. Alright, we're gonna let Claude cook something up here, and I'm gonna take a quick break and go to the bathroom. Don't let us down, Claude. One time, come on. But before I go to do that, let's add a podcast. Let's see what Lex is up to. Lex, where are your podcasts? There we go. Lex Fridman. Okay. Jensen Huang.
The following is a conversation.
The architecture could attract enormous aperture.
The following is important that this is such a fascinating problem because customer problems, the bulk of them fall into very specific set of categories, but there's nuanced details within those categories that make all the difference. And it can be an incredibly frustrating thing for a human being like myself, I swear. I promise. Definitely not a robot. Wouldn't tell you if I was. But it's frustrating for a human to come to the customer service process and to know that your problem kind of is like this problem. There's all these details that you can provide about the system you're operating on, the specifics of the puzzle you're trying to solve. But there's details that you just know in your gut that this is important, especially if you kind of thought through the problem. I've been through this quite a bit. You want to have some level of personalization that can get to the tricky aspect, the perspective on the problem that really would lead you down the road to a solution. Anyway, love this problem. Really glad Finn is focusing on it. Go to fin.ai/Lex to learn more about transforming your customer service and scaling your support team. That's fin.ai/Lex. This episode is also brought to you by Quo, spelled Q-U-O. Also known as a company with just 3 letters, will win you a game of Scrabble. That is not a joke. It feels like a joke I have made before, but let's run with it. It's a dad joke. It's a bad dad joke. The only thing worse than a dad joke is a bad dad joke. But here we go. Spelled Q-U-O, a business phone platform for calling and messaging. Basically, you have a bunch of people trying to help a larger group of people, and you want to orchestrate how they communicate with each other. And this is just the system that does it extremely well, period. Quo integrates AI into the whole shebang, organizing everything, generating summaries, highlighting the next steps, all that kind of stuff. It just does it well. The interface on top of the AI is also really strong. So try Quo for free, plus get 20% off your first 6 months when you go to quo.com/Lex. That's Quo.com/Lex. nerdist.com/Lex. This is the Lex Friedman Podcast. And now, dear friends, here's Jensen Huang. You've propelled NVIDIA into a new era in AI, moving beyond its focus on chip scale design to now rack scale design. And I think it's fair to say that winning for NVIDIA for a long time used to be about building the best GPU possible. And you still do, but now you've expanded that to extreme co-design of GPU, CPU, memory, networking, storage, power, cooling, software, the rack itself, the pod that you've announced, and even the data center. So let's talk about extreme co-design. What is the hardest part of co-designing a system with that many complex components and design variables?
Yeah, thanks for that question. So first of all, the reason why extreme co-design is necessary is because the problem no longer fits inside one computer to be accelerated by one GPU. The problem that you're trying to solve is you would like to go faster than the number of computers that you add. So you added, 10,000 computers, but you would like it to go 1,000,000 times faster. Then all of a sudden, you have to take the algorithm, you have to break up the algorithm, you have to refactor it, you have to shard the pipeline, you have to shard the data, you have to shard the model. Now, all of a sudden, when you distribute the problem this way, not just scaling up the problem, but you're distributing the problem, then everything gets in the way. This is the Amdahl's law problem, where the amount of speed up you have for something depends on how much of the total workload it is. And so if computation represents 50% of the problem, and I sped up computation infinitely, like 1,000,000 times, I only sped up the total workload by a factor of 2. Now, all of a sudden, not only do you have to distribute the computation, you have to, shard the pipeline somehow, you also have to solve the networking problem because you've got all of these computers are all connected together. And so distributed computing at the scale that we do, the CPU is a problem, the GPU is a problem, the networking is a problem, the switching is a problem, and distributing the workload across all these computers are a problem. It's just a massively complex computer science problem. And so we just got to bring every technology to bear. Otherwise, we scale up linearly or we scale up based on the capabilities of Moore's law, which has largely slowed because Dennard scaling has slowed.
I'm sure there's trade-offs there. Plus, you have a complete disparate disciplines here. I'm sure you have specialists in each one of these: high bandwidth memory, the networking, the NVLink, the NICs, the optics and the copper that you're doing, the power delivery, the cooling, all of that. I mean, there's like world experts in each of those. How do you get them in a room together to figure out?
That's why my staff is so large.
What's the can you take me through the process of the specialists and the generalists? Like,
better.
or node editor or node
Webflow is the only one platform that allows to create production-ready apps in no code.
No double instantiation. Should return exactly one result, the state object in content view if when the app and verify library loads all content, search bar filters. Should stay very relevant at a podcast feed. Read. Create a Swift UI view named add content view. State variable. Create a Swift UI named add content view with the following structure. Tapping plus opens add content view.
Webflow is the only one platform that allows to create production-ready apps in no code. And how we came to the product, basically, the story is that we all were trying a lot of vibe coding tools, and 2025 is the year of vibe coding, in my opinion. So we were trying a lot of tools like Lovable, Bold, Replit, V0, and all these AI app builders. And we realized that they were super cool. They had this wow effect on the front-end side, but on the back-end side, they were really, really weak. And yes, some of them, like Replit, they were a bit better, and they were offering already a bit more structure. But at the same time, when you are a non-technical person and you want to actually understand what's going on, and you have
Welcome to this original
competing for relevance. So what does this quantum classical hybrid actually...
Welcome to this original series from Quiet. Welcome to this original series from...
In a hybrid solver, the classical computer acts like a disciplined conductor. It prepares the problem, chooses parameters, and measures the quantum output. The quantum processor then explores a landscape of possibilities in superposition, using entanglement to sample correlations that are brutally expensive for classical methods alone. Think of it as asking a room full of very strange musicians to improvise the hardest part of the score, while the classical system keeps perfect time and corrects the rough edges. The hybrid approach is especially compelling for optimization, chemistry, and machine learning, where the search space explodes faster than ordinary brute force can handle. A quantum subroutine can propose a promising configuration, and the classical optimizer can refine it, test it, and feed back the next guess. That loop is the magic. Quantum for depth, classical for control. It is not louder than a thunderclap. It is more precise, like a watchmaker hearing the tick of a single misaligned gear. And the timing could not be sharper. Market watchers have recently noted renewed investor attention around quantum names, with D-Wave shares jumping on Monday before broad reversals later in the week. A reminder that the field is still volatile in both technology and sentiment. CEO NCBSEPNCN 999. Meanwhile, security teams are watching the other side of the horizon as the push toward quantum-safe encryption accelerates, because future quantum machines threaten today's public key systems. CEO NCBSEP, in other words, the classical world is already adapting to the quantum one. From where I stand, the future is not quantum versus classical. It is quantum plus classical, each doing what it does best, each covering the other's blind spots. That is the real breakthrough, and it is already unfolding in the lab, in the cloud, and in the algorithms we are learning to trust. Thank you for listening, and if you ever have questions or topics you want discussed on air, just send an email to leo@inceptionpoint.ai. Please subscribe to Quantum Computing 101. And remember, this has been a Quiet Please production. For more information, check out quietplease.ai.
Quietplease.ai.
Hear
Hear what matters.
what matters.
Welcome to this original.
Researchers at Google Quantum AI and collaborators at UC Santa Barbara announced progress on a quantum classical hybrid workflow for optimization using superconducting qubits guided by a classical AI model to route data traffic in simulated data centers more efficiently. Think of it as pairing a chess grandmaster with a lightning-fast analyst. The quantum chip explores bizarre superposed configurations, while the classical system judges which moves are worth pursuing. Here's how this hybrid solution really works. On the quantum side, they run a variational quantum algorithm. You send in a set of parameters. The qubits evolve through tunable gates, and you measure them again and again, harvesting noisy probabilities. On the classical side, a powerful GPU cluster ingests those measurement outcomes, updates the parameters using standard optimization tricks, then sends a new guess back to the chip. Quantum proposes, classical disposes. Together they spiral toward a low-cost solution that neither could find as efficiently alone. The room where this happens is a sensory paradox. The fridge housing the qubits is colder than deep space, yet just a few meters away, classical servers radiate a dry electronic heat, and the air smells faintly of metal and coolant. On one monitor, I see waveforms, microwave pulses sculpted with absurd precision.
I was on Twitter on X the other day. I saw like this. There is this guy who has this website where you can check. Like he's sharing ideas, and then you're free to take them. I think it's called Heisenberg or something like that.
Yeah, ideabrowser.com.
Yeah, idea browser, exactly. And there was this idea of a domain, like a website where you can find domains that are valuable, that are going to expire. Was an idea just there. And I saw a guy just pick the idea the day after the idea was ready, and he started pushing it. And he's doing, I don't know, already $1,000, $2,000 MRR, like from idea to execution and money in a couple of days. So we are already in a way there. And this is going to just accelerate. So I think the time is now to do something. The more you wait, the easy, the low-hanging fruit would be gone.
Yeah, I saw that as well. Namesnag.com.
Namesnag, exactly. That's crazy.
Yeah. We definitely share similar needs. So when you say that the time is now to do something, what are you referring to specifically?
Anything really. Like it's always a trade-off, right? Like you're trading your time. Like if you work, like a normal job, a 9 to 5, you think you're safe. Like that's the way that we were told growing up.
Status. Should I stop working on this now? Man, I don't know. It's hard to want to stop. I guess we're gonna stop now. While I'm ahead, I'm gonna stop. See you next time.